Welcome back to Larry's Classroom. We're going to continue with learning a little more about analyzing, a little more practice of analyzing series circuits. We're going to start with a series circuit. Two resistors and a power source. We got 60 volt power support source. We got R1, which is 20 ohms. And we have R2, which is 10 ohms. We want to find out the voltage across each resistor, the power dissipated by each resistor, and the power supplied by the power supply and all that. So the first thing you want to do when you look at any circuit actually, but a circuit like this, what do we have? We have the voltage supplied, we have the two resistances. If we want to find out power or voltage drops across resistors, we're going to need current. So let's go to our current formula, which we have I for intensity is the voltage divided by the resistance. Now you probably remember from before that we have our total voltage of 60 volts. We need to divide it by the total voltage of our total resistance. So let's figure out the total resistance. Resistance total equals 20 ohms plus 10 ohms equals 30 ohms. Now the voltage total, we can call this voltage total, the supplied voltage, is given to us. So if we want the current, we're going to go I equals VT over RT. VT was given to us, 60 volts. RT we just calculated, 30 ohms. And 60 divided by 30 is 2. So we have 2 amps. So let's add that to our drawing here. Let's just put a little 2 amp and a little arrow over to indicate the direction of the current. It's flowing from negative to positive around the circuit. Now we'd like to know the voltage across each resistor. So let's take a look at R1. Well, the voltage is voltage equals IR. We've been talking quite a bit about IR drop. It means current times resistance. We've calculated the current, 2 amps. The resistance is 20 ohms. So that's 2 amps times 20 ohms gives us 40 volts. Let's calculate the voltage across R2. You're probably already thinking, we'll multiply the current times the resistance, and you'd be correct. So we'll write down here R2 voltage. Again, we're using the same formula, IR drop, voltage times resistance, gives the voltage applied or the voltage dropped across the component. Current same in a loop, so we got the same current. 2 amps, and we're going to multiply that times now a different resistance, which is 10 ohms, times 10 ohms, and that gives us 20 volts. Let's call this V2 and this V1. They relate it to the component which appears. Now you remember our voltage total equals V1 plus V2 and so on for every voltages you got in your loop. We only have two. V1 was 40 volts, plus V2 we calculated to be 20 volts, and that equals 60 volts, which you see is consistent with the applied voltage. The voltage supplied by the source applied across the circuit is equivalent to the sum of the voltage drops around the loop, or through the loads. So we've calculated, we started out by looking at what we had, and we realized we needed current to do the rest of it. Let's calculate the power on each of these components. Well, power 1. That's the power dissipated by resistor 1, and we're going to say that's a P. I want a P there. Power 1 equals, we're going to start with the current times I1 times V1. We got a single current, so I don't need to set it off from any other currents. But we had power 2 amps for current times our V1, which was 40 volts. That equals 80 watts. Now we're going to use our other formula too, which is power 1 could also be I squared times R1. Remember that power equals I squared R. That was one of our power formulas. The current squared times resistance gives us our power. Well, 2 amps again. So we got the 2 amps, and we're going to square that. We're going to multiply that times the 20 ohms. So that becomes 4 times 20 equals 80 watts. So you notice they're consistent. The two different power formulas gave us the same power dissipated across this R1. So we're going to write up here, we're going to say V1 equals 40 volts and P1 equals 80 watts. And it's a good thing we got the same answer this way. If not, that would have indicated we made an error somewhere, because a given resistor at a given time cannot be dissipating two different levels of power. And we're gonna look at the power on R2. We're gonna call that P2, and we're gonna use the same formula IV for our. Let's add that up here too. Power equals current times voltage, which we used that formula here, but I wanted to put it up here for reference. So we're going to say I, and now we're going to put V2, because the current's the same for both of them, so we only have a single value for I, but we do have a different voltage across R2. And I, so it's still 2 amps. And we have a resistance of 10 ohms. Or no, we want a voltage drop. We calculated voltage across R2 of 20 volts. So we have 2 amps times the 20 volts that's dropped across R2, or dissipated by R2, gives us 40 watts. And let's use this other formula, the I squared R, this one here, the other power formula. I squared times R. You notice for this formula, we need current voltage for power. For this formula, we need current resistance. So we depend on which one we have, maybe which one we chose, but we have already calculated the voltage and calculated the the current, we have both. Though we could have chose to calculate power first and not calculate the voltage by using this formula. But we have 2 amps everywhere in a series circuit times the resistance, which was 10 ohms. And that equals 4 times 10 equals 40 watts. And once again, we have consistency, the same value. So let's write this down here. We have V2, which we calculate here to be 20 volts. And we have power 2, which we calculate using 2 different methods to be 40 watts. And just for completeness, let's calculate our current, or our power supplied by the power supply. Well, we can use 2 different choices here. We can use the power equals IV. So let's do that first. Let's use the power equals current times voltage. And we'll say power from the total power from the source is equal to I times the voltage of the source, VT. Well, the current 2 amps, as always, 2 amps times the 60 volts. That equals 120 watts. Now you notice over here I had 80 watts and 40 watts. And 80 plus 40 does add up to 120. So they're consistent. But let's calculate this power from the source using the I squared R formula. So it equals I squared times the total resistance, which we calculated here to be 30 ohms. I squared R, and now we had 2 amps squared times 30 ohms, and that ended up being 4 times 30 equals 120 watts. So what you see here is, as long as we ain't making errors, either formula leads us to the same place. We found 120 watts supplied using the I squared R formula. We found 120 watts supplied using the I times VT, voltage total formula, the voltage of the source. And over here we found that we had 80 watts plus 40 watts dissipated by the 2 resistors. So we have that the 120 watts supplied by the source is equivalent to the 120 watts dissipated by the combined loads in the circuit. We started out, we had the resistances, we had the voltages, we did not have the current, so we used the total resistance formula to come up with the total resistance. We divided by the supplied voltage, VT, divided by the RT, total resistance, to get 2 amps. And that gave us all the information to solve anything we needed to know. And we actually had 2 ways to solve each of the power values. We used the IR, or the IV, or the I squared R. So we kind of covered that, I think, what this circuit was about. We'll talk a little bit more about how to go about analyzing a series circuit. Well, first thing you want to think about is, if you know I anywhere, you know I everywhere in a series circuit or a loop. So it's important to remember that the current is the same everywhere in a loop. If you're given the current, that's a nice thing. If not, maybe there's a resistor that they've given you the voltage value about across or something, so you can find the current. You're going to need the current to solve a series circuit. And so basically we're going to calculate I either by using I is equal to VT over RT, or you might calculate it by, because they gave you the resistance sum component and the voltage across, so maybe they'll give you the voltage across R1, say, we call that V1. I is equal to V1 divided by resistance 1, R1. You're basically going to use this voltage and resistance somehow to find a current for the loop. 3. Once we know I, we can calculate the IR drop across each resistor in the circuit. I'll just say IRs, and we'll have the right voltage drops. And we can use our formula for total voltage, VT equals V1 plus V2 plus all up to Vn, however many components you have. And if you're given VT and you're able to find all but one of these, you can solve for that missing one. If you're not given VT and you're able to find all of these, you can add them up to get VT. So you're gonna remember that if you know the current in one spot, you know it everywhere. We're going to calculate currents using either V total divided by R total, or I'm going to make this be Vn and Rn, because any component that you have the voltage across, if it was component resistor 3, we'd say that would be V3 and the value of R3. Any component that they've given you the voltage across and the resistance of, you can calculate the current. And being current is the same everywhere in a loop or a series circuit, which a simple series circuit is a single loop, you will know the current everywhere. Now you can use this known current to calculate voltage drops across each resistor, and you can use this total voltage formula to solve for any one you may not know. So that's kind of your general idea of methods of how to solve a series circuit. Now we'll spend some time trying to apply these. We're going to draw a series circuit, and we're going to have a VT equal to 120 volts. And it'll be a positive supply, or a DC supply. We're not going to draw the battery symbol. Maybe it's coming from some kind of a power supply other than battery. We're going to put 3 resistors in here. We're going to call these R1, 15,000 ohms, 15k ohms. We're going to say R2 equals 20k ohms. Now, we don't know the value of R3, but we are given the current through R3, 2 milliamps. And of course that's traveling from negative to positive, it's electron flow. So what do we have here? We have 3 resistors, 2 of which we know the value of, 1 of which we do not know the value of. And We have a given voltage. We also have a given current. Now, because this is a loop or a series circuit, we know this 2 milliamps is everywhere. So we can go ahead and put that here. And just for a reminder, a milliamp is 1/1000th of a volt or of an amp, or milliamp is 0.001 amp. We'll write that up here. Milliamp equals 0.001 amps. So we could solve this two different ways, really. We could calculate the, well, it looks like we really only have one choice here. Well, there's a couple choices. We could calculate the voltage drops each case, the 2 milliamps times the 15,000 ohms, and the 2 milliamps times the 20,000 ohms. Let's go ahead and do that. V1, it will be I through resistor 1 times R1, the value of it. Well, we have 2 milliamps, which we could also call that as 2 times 10 to the negative 3 amps. Because if we took the 0.002, or we took the 2 milliamps, and we moved the decimal place 3 places to the right because negative, we'd end up with that 0.02 amps. And we could take this R1, which is 15,000 ohms, and we can write that as times 15 times 10 to the third ohms, because 15,000 ohms, 15k ohms, is equal to 15 times 10 to the third ohms. Well, that's basically moving this place 3 places to the right instead of the left like we did up here. 15000, 15,000 ohms. Now what we're kind of getting at here, we're putting these in the scientific notation, 10 to the negative 3 times 10 to the positive 3 cancels out to just being 1. The negative exponent cancels out the positive exponent. We basically end up with 2 times 15 equals 30 volts. So when you're multiplying milliamps times k ohms, you can just do it directly. 2 times 15, 30 volts. Let's write that here. Let's write V1 equals 30 volts. And it's because of this cancellation of these 10 to the negative 3 and the 10 to the third exponent. Which is kind of handy to remember that. I'll write that here. Milliamps times k ohms equals volts. Save you some calculations or some complexity in your calculations. So let's figure out what the voltage here is for across R2. V2 equals, and let's just use our milliamps times k ohms here. 2 milliamps, to save ourselves a little effort, times 20 k ohms. Basically 2 times 20, 40 volts. So what have we done here? We figured out that there's 40 volts here for V2. And why do we do that? Well, so now if we want to, we can find R3 by calculating the voltage on R3 and then using our resistance formula, which basically we have that R equals V over I. This is part of Ohm's law. The resistance, one form of Ohm's law, the resistance equals voltage divided by the current. We've been given the current. We know the total voltage. We can use the VT. VT in this case is going to be V1 plus V2 plus V3. We can calculate V3, then use this formula to find the resistance of R3. So let's go ahead and do that. VT, 120 volts, plus V1 we calculate to be, or equals, excuse me, V1 we calculate to be 30 volts, V2 we calculate to be 40 volts, so we're going to add 40 volts, plus whatever V3 is. We don't know what V3 is yet, but we're trying to find out, plus V3. Now, we can do a little bit of simple algebra here. This is an equation, the equal sign, and we know that 120 volts is equal to whatever's over here. Well, we want to get the unknowns, the V3 by itself, and all the knowns, the voltages, over to the left. Now, you can, as long as you do the same thing in every case to both sides of an equation, it will still remain balanced, be equal. So let's subtract 30 volts here, and subtract 40 volts here, and subtract 30 volts, and subtract 40 volts from the other side. So what do we get here? We now have 120 minus 30 is 90, minus 40 is 50, so we basically end up with 50 volts is equal to, well, 30 volts minus 30 volts is 0 volts, 40 volts minus 40 volts is 0, equals 0. So basically we have is that V3 is equal to 50 volts. So we could put that here. So what have we done? We use the given current and the given resistances to calculate the voltage drops on these two resistors. Then we use our voltage summation formula to find out how much voltage we needed here to make this true. And we found that we needed that 30 volts. And let's go ahead and check that out. If we take the VT equals V1 plus V2 plus V3, well, we have 120 volts, VT given, equals V1, which was 30 volts, plus V2, which was 40 volts, plus V3, which we just found to be 50 volts. Well, 120 volts, 30 plus 40 is 70, plus 50 equals 120 volts. So we found the voltage across R3 using our series voltage formula. And now we've kind of checked back to make sure that it was right. It looks like it was. So now we have the current and the voltage. Well, we can find R3, the resistance, can't we? Because we have the resistance equals voltage divided by current formula. So let's say that R3 is equal to voltage 3, V3, over the current of 2 milliamps. So let's go ahead and put V3 in there, 50 volts, and the 2 milliamps. And by the same token, when you got voltage in milliamps, you'll get, it'll come out in K ohms. So basically 50 divided by 2, 25 K ohms. Now if you didn't like doing it that way, you could say 50 volts divided by 0.002 amps, which is what 2 milliamps is represented as amps. and you would get 25,000 ohms. But 25,000 ohms and 25 k ohms are two ways of representing the same resistance. So we found R3 in that fashion. Let's find R3 in a little bit different fashion here. Let's go to our series resistance formula. Resistance total equals resistance 1 plus resistance 2 plus resistance 3. We have three resistances to deal with here. So let's see what we got. We're given R1, we're given R2, we're not given R3, and we're not given RT, but we can calculate RT because we have resistance equals voltage divided by current. Well, what is our voltage total? That resistance total equals voltage total divided by current. Our voltage total, 120 volts. And we're going to divide that by the 2 milliamps. Which this should be 60 k ohms. Voltage divided by milliamps gives us in k ohms. And let's see. That's the total. We calculated R3 a little bit ago to be 25K, so let's put that in here. We didn't write it up here. Let's write it up here. Now let's use our series resistance formula. RT is equal to R1, which was given, which was 15K ohms, plus R2, which was given, which was 20K ohms, plus R3, which was given to us to be, well, we didn't know that, did we? But we just calculated. So let's use what we calculate here. 25 k ohms. So let's add that up. RT equals 15 plus 20, 35, plus 25, 60 k ohms. So what we're showing here, we calculated RT, we used our solve value for R3 along with the given resistances and found they added up to the same. Now another way we could have done this, if we hadn't calculated R3 first, we could have said, we could have taken the same formula, RT equals R1 plus R2 plus R3. Well, RT was, we just calculated to be 60K. And R1 was given to us as 15K. R2 was given to us as 20K. R3, we didn't know, so we'll just leave that as a variable, R3. Now we'll subtract that 15K from both sides. Minus 15K, minus 20K. Both of these known values, we'll get them over to the other side. We're going to take minus 15K, minus 20K. So 60 minus 15, that leaves us with 45, minus 20, that leaves us with 25 k ohms, which is what R3 would be. So we calculated current, we calculated voltage drops, we found the voltage drop across R3 and used that to calculate the resistance. The other thing we did is we took the given voltages, the given current, calculated voltage drops, found the we used the voltage and current to find out what the total resistance would be, which we did here, and found a way to get R3 by solving the series resistance formula. Over here we solved the series voltage formula and got a voltage across R3, and we were able to calculate the resistance of R3 using this formula right here, voltage over current. In this case, we calculated the total resistance of the entire loop with the applied voltage and the given current, and then we used the series resistance formula to solve for R3. So there's often multiple ways to solve these things. You want to look at the circuits and try to figure out, what works best for you. A couple more things here I want to talk about related to series circuits. Sometimes you might have a desire to put a resistance in series with a known load in order to run that load up a higher than the normal voltage supply. So we're going to start with a little circuit here. And we're going to put a 12 volt DC supply. And this time I put the positive up here. And we're going to put some resistance, which we'll call RS for our series. And our load is basically a transistor radio. And that radio, we know, normally operates on 9 volts and requires 20 milliamps of current to run, which is also equal to 0.002 amps. So we want to do, using that 20 milliamps, first we want to figure out how much voltage we want to reduce, which voltage we want to see drop across RS. So let's start with that. We'll use our series voltage formula again. We have that VT is equal to V1 plus V2 and so on. We're going to say that V1 equals the resistance across the voltage dropped across RS, and the V2 equals the 9 volts needed to run this little radio. Well, VT is given to us, so VT is 12 volts. V1 is what we're trying to find. We don't really know what that is yet. We do know V2 because it's given to us, plus 9 volts. Again, we'll take this equation, we'll do the same thing to both sides, which in this case will be subtract 9 volts from each side, which will keep it balanced and keep the equation to be true. Well, 12 minus 9 is 3, so we got 3 volts is equal to V1. So we need to drop 3 volts here. So we need to figure out is what value of resistor we need to have an IR drop of 3 volts when the radio is drawing the 20 milliamps that it takes to operate. That will leave the other 9 volts to run the radio as it should be. So we'll remember that V equals IR. We don't know R, so we're gonna go to we're gonna say that R equals V over I. That's another form of Ohm's law. Well, we know that we need 3 volts, and we know that I is 20 milliamps. So we'll put 3 volts, and we're going to put this in the form of amps, 0.002 amps, and we end up with a resistance of, we need 150 ohms. And let's double check that using this formula. Voltage equals I times R. So we have here that 0.002 amps times 150 ohms. Let's see. So 2 ends up being 300, and we move our decimal place Oh, let me just do it with a calculator, make sure I'm doing it right. Oh, okay, I see. I see. This is, I put 2 milliamps. That's why it didn't look right. This is two milliamps, or 20 milliamps. Excuse me. So we end up with, let's just put 0.02. 0.02, the 2 times 150 gives us 300, and then we'll move the decimal place 2, so we have 3 volts. So our 150 ohm resistor in series here, let's write that 150 ohm is what our series will be. So by putting a 150 ohm resistor in series with this 9 volt 20 milliamp radio, we are able to run that radio from a 12 volt supply. And what this illustrates is, to figure out, we often call this a drop-in resistor, to figure out the value of a drop-in resistor, you need to know what current your load would normally draw. If you had a larger current, it would take us, you wouldn't need as big a resistor to drop the required 3 volts. If you drew lesser current, you would need a much bigger resistor to drop the required 3 volts. If you think about it, voltage equals I times R. If we're looking for the same voltage, if we make the current smaller, we got to make the resistance bigger to get the same result in our multiplication. If we make the current greater, we got to make the resistance smaller to get the same result in our multiplication. So the current of the load is required. You need to know that to calculate a proper series drop-in resistor to run a load off a larger voltage. And of course you need to know the required voltage and the available voltage of your supply, so you figure out how much voltage you need to drop there. Now we're looking at a case where we got more than one voltage source in series. And this is very similar to our series aiding stuff that we did a little bit ago. Minus and plus. This is V1, which is 2 volts. And now this plus and minus, which V2, which also equals 2 volts. And this is 10 volts, this supply. And we have R1, which is 3K ohm, 3K ohm. R2, which is 5K ohm. R3, which is 2K ohm. What we can see here, we'll use our R total equal to R1 plus R2 plus R3, which we only have 3 here. So we have 3K plus 5K plus 2K, 3K plus 5K plus 2K, which basically 3K plus 5, that is 10K ohms, or 10,000 ohms. Now let's look at our voltage sources. we have 10 volts here, and this will be series 80 because it's plus or minus, so that gets up to 12 volts. But this one is series opposing, which takes us back to 10 volts. So basically these two power sources, being their opposite polarity, cancel each other out. So we have a total of VT equal to 10 volts to supply this load. It's pretty easy to see that the positives are connected together through R1 and the negatives are opposite, so they don't, any current supplied by V2 is canceled out by current supplied by V1 because it'll be in the opposite direction. You remember we spoke about superposition a little while ago. That's one way to look at that. Another easier way to look at it is just figure out the total effective voltage, and let's just draw it that way. This is R2, also R3. No, this is R2, and this is R3. R2, that was 5k ohm, and this is R3, which equal 2k ohm. This is 10 volts. Now we've only got a single voltage source, and we did that because these two cancel their potential difference out, so it has no impact. Negative, positive, we know that our current flows in this direction, our electron current flow. We want to find out what that electron current flow is. We add up the voltage sources, which we did up here, found 10K. We have I equals V over R, and our V was 10 volts, and our R was 10 K ohms. And again, voltage and K ohms, we can just go straight to milliamps. We don't have to. So that basically is 1 milliamp. So basically now we know that there's 1 milliamp in this circuit. And it's the same here. And when we saw that these canceled, we just took them out of the circuit and made the calculation a little bit easier. So let's think about what happens if we have problems with a series circuit. We'll draw a little series circuit and we'll talk about what can happen when it doesn't work correctly. So I've got a 120 volt supply, and we have a resistor R1 equal 50 volts. R2 equal 50 ohms, excuse me, 50 ohms. R2 equals 40 ohms. R3 equals 30 ohms. So let's first just calculate the current when everything's working normally. 50 volts or 50 ohms plus 40 ohms is 90 ohms plus 30 more ohms. So we got 120 ohms. So our total equals 120 ohms. 50 plus 40 plus 90. 50 plus 40 equals 90, plus 30 equals 120. So we've calculated just by adding the three resistors up, the three series resistors using the series resistance formula, which I believe you probably know by now. R total equals R1 plus R2 plus R3 on out to Rn. The total number that you might have. In this case, we had 3. We put the 50 and the 40 and the 30, and we added them up, we got 120 ohms. Let's calculate the current. I equals voltage divided by resistance. We got 120 volts. We got 120 ohms. Well, that's pretty simple math. It's 1 amp. So when everything's merrily rolling along, this circuit has 120 volt supply, 120 ohms, has 1 amp. So let's go ahead and write that 1 amp up here. And again, this is electron flow. It goes from negative to positive, so it's going to be in that direction. So let's see what happened. Oh, let's do one more thing here. Let's calculate the voltage across each. V1 equals R1 times I, which is basically 50 ohms times 1 amp equals 50 volts. So we got 50 volts. V1 equals 50 volts. V2 equals R2 times I equals 40 ohms. 40 times, again, 1 amp equals 40 volts. So we're going to say V2 equals 40 volts. V3 equals R3 times I, which was 30 ohms, times 1 amp, 30 volts. Now if we apply our V total, our series voltage formula, we have that VT equals V1, which is 50 volts, plus V2, which is 40 volts, plus V3, which is 30 volts. So we just calculate all of those. And that basically adds up to 120 volts. 120 volts, so the total IR drops across the loads, which is equivalent to the 120 volts supply. That's the circuit running along happily. Let's see what happens if we get a break in that circuit. Well, we get a break in that circuit. Now the resistance total is basically infinite. So the current basically drops to 0. Let's look at each of our voltages across V1, V2, V3. If the current is 0. V1, 50 times 0. V1 becomes 0 volts. V2, 40 ohms times 0. V2 becomes 0 volts. V3 is the 30 ohm resistor times the 0 current. V3 also becomes 0 volts. Now our series voltage formula, VT equals V1 plus V2 plus V3. Well, this still has to be true. So 120 volts equals 0 plus 0 plus 0. 120 volts equals 0 volts. That don't make sense. So where did that voltage appear? Well, we have it all appears right across here. Well, let's call this VB, the voltage of across the break in the circuit. So let's put a VB on here, voltage of the break. 0 plus 0 plus 0 plus VB plus VB. So what we find out here is that 120 volts is equal to VB. So we basically have the full 120 volts appearing right here. When there's a break in the circuit, all the voltage appears across the open. And suppose that this was just a switch that we could open and close. We'll draw a switch in here. We close the switch. Now all our voltages appear across each of these resistors as we calculate over here. Our 120 applied is the same as all these voltages adding up. All is good. So when the switch is closed, if we put our meter across there, there ain't no voltage drop there because it's all appearing here, 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 here. But if we open the switch, all of these voltages go to 0, and now instead of calling it VB, let's call it VS for V switch. And we'll change that thing here to say VS. VS, V switch, VS, V switch. So what we're getting down to is an open switch in a series circuit like this. All of the supply voltage will appear across that open switch. So if we put our meter here, we read the full 120 volts. We close the circuit. Now our resistance is essentially 0. No matter what the current is, we should see 0 volts. And our voltage drops appear again in the places where we expected them to be. So a good switch in operation closed, you put your voltmeter across it, you read 0 volts. A good switch, when it's open, you'll read the full voltage. If you have a switch that you think is good and you know it's in the closed position, but your circuit is not operating, if you read the voltage across that switch and find anything much more than 0 volts, something close to the supply voltage, you know that contacts in that switch have failed because it's now become a high resistance, and by the IR drop, the current times the really high resistance gives you a lot of voltage. So I'm going to write that down to kind of help you remember it. Good switch. Good switch. Closed. 0 volts. Open. I'm going to say full voltage. Bad switch. Closed. Full voltage, because if the switch has failed, it doesn't actually close. Open. Same thing, full voltage. Because now the switch is supposed to be closed. A switch that is closed and working will have 0 volts across it. The switch that's closed and not working will have lots of voltage across it. So that's one way you can kind of tell when there's a problem with a switch. Now we're going to do a quick little talk about some logic related to series circuit. So we got one more series circuit we're going to talk about, and I think we'll be done. We're going to put a 6-volt battery, and we're going to put two switches in there, which we'll label switch A and switch B. And we're going to put a light bulb in there. It's designed to run on 6 volts. So if you close both of these switches, you get current flow through the light bulb lights. You open either one of them, you interrupt the current, and the light bulb does not light. Let's think of this like a truth table. Say switch A, switch B, and we're going to say lamp. We'll call the light a lamp. Switch A, open. Switch B, open. The lamp will be off. Switch A open. Switch B closed. Still the lamp will be off. Switch A closed. And switch B open. still the lamp will be off. Switch A closed and switch B closed. Now the lamp will be on. This is not how we build logic gates, but this is a wired and logical function. So this circuit will perform the AND function using a couple of switches. That's what we call it, a wired AND function. Now, if we say that open equals 1, let's say open and on equals 1, and close and off equals 0. So a switch open, logic 1. Oh, got that backwards. I want this to be, closed. Closed and on is 1, open and off is 0. So if a switch is closed or a lamp is on, we call that a logic 1 in this case. If a switch is open or the lamp is off, we call that a logic 0. So let's make a truth table using 1s and 0s. We'll go A, B, and lamp again. Let's just call it output. Let's just call it output. 0, 0, 0. 0, 1, 0. 1, 0, 0. And 1, 1, 1. So basically we've created two truth tables for basically the same function. This is a more like you might have seen before with binary 1s and 0s. Here we have opens and offs. The open was 0, so open, open, and off, 0, 0, 0. Open was 0, closed was 1, and off was 0. Closed was 1, open was 0, off was 0. Closed, closed, and on were all 1s. So we're showing this AND function is we need truth for both inputs to get the true output. And we're calling closed and lit to be closed and on to be true in this case. So we've shown how to create a logical AND function with a series circuit. And we've shown a truth table using the terms open, closed, and off. And we've converted the same truth table using these little conversions to 1s and 0s. And this is, like I said, in a digital logic chip, this is not, they don't have little switches and such, but this is still the function that's performed there, if it's an AND gate. And let's see, I will show you the symbol for an AND gate also. And I'm going to call this out to match up the truth table we had, but we had the A and B in the out. I'll draw that truth table one more time. And what you see is it's AND gate. And we need a true on both inputs of the AND gate to get a true on the output of the AND gate. And we showed a simple way of implementing that with a series circuit, though it's not what you're going to find in your little computer chips, but it does the same kind of a function. Anyway, I think we'll call that good for the day. Be sure to like and subscribe. And until the next time, keep on learning. Now, I'd like to make just a single correction, really. In this last lecture, we're talking about calculating a series dropping resistor around a transistor radio. I made the statement that 20 milliamps was equal to 0.002 amps. That is completely incorrect. This would be the equivalent of 2 milliamps. So we're going to cross that out. I did that at about 36 minutes and 55 seconds into the video, and the true result, 20 milliamps, would be equal to 0.02 amps, or you could also write that as 0.020 amps. And you see this here portion is the milliamp. That matches the 20 milliamps. I made the same mistake again about 39 minutes and 18 seconds into the video, and a little bit later, 40 minutes and 19 seconds into the video, when I was calculating the resistance, I caught my error because it wasn't coming out right, but I did not go back to my earlier drawings, which were still on the board, and edit this 0.02 to say 0.002 to say 0.02. So 20 milliamps is equal to 0.020 amps. 20 milliamps does not equal 0.002 amps. I just wanted to correct that so no one would be confused. Anyway, thanks for listening again.